This video introduces the universal introduction rule, one of the basic rules for proofs in QL. We're in the midst of introducing the proof system for QL. Recall that the proof system for QL takes the proof system for SL and it adds four new basic rules, an introduction and an elimination rule for each quantifier. And it will also add one new derived rule. In the last video, we covered universal elimination and existential introduction. This video will cover universal introduction. Consider this argument. For all x px, for all x px arrow qx, therefore for all x qx. If you think about what it would mean in English, it's obviously valid. But what would it take to give a proof of it? Our universal introduction rule should allow us to draw conclusions like this. But how should it work? Let's set up the proof in the usual way. We write down the premises. They're universally quantified sentences, so we can use universal elimination. For example, if we pick the constant a, we can write down PA and PA arrow QA. Well, those two things, lines 3 and 4 together, allow us to write down QA by arrow elimination applied to lines 4 and 3. But that only shows QA, and the conclusion we want is for all x qx. This really doesn't feel like enough. I mean, you're probably tempted to say, look, to show that everything's a q, it takes more than showing that one thing, this a, whatever a is a q. It really feels like we need more than that. Well, okay, we've done it for a, we could also do it for b. And the pattern of reasoning is going to be exactly the same. We get PB and PB arrow QB by universal elimination. And then we get QB by arrow elimination. And once we've done it for B, we could do it for C. Again, same steps. Universal elimination twice, arrow elimination gives us QC. And then we can do it for D. Universal elimination twice, arrow elimination gives us QD. And of course, we could keep going. I'm not going to keep filling this video with a proof of QE and a proof of QF and a proof of QG. Eventually, we'll lose patience. We know that we'll never be able to do it for all of the constants because there are infinitely many constants. Trying to do it by proving it for every single constant would take literally forever. So the question is, when, if ever, should we be allowed to conclude for all x qx? If you're thinking about the semantics, for all x qx says that every member of the universe of discourse is in the extension of Q. And there might be infinitely many things in the universe of discourse. But remember, we're not working in the semantics. In a proof, there is no universe of discourse. There are only sentences and rules. Once you see lines 3 through 5, you have a pattern for proving that anything's a Q. Lines 3 through 5 give us a kind of recipe. Once we did it for A, we could quickly do it for B, C, D, and as many more as we wanted. The key here was that we showed it for QA, and A wasn't anything special. It wasn't anything in particular. On lines 3 through 5, we could see A not serving as the name of a particular thing, a particular object, maybe Alvin, but instead it's a placeholder. It's a dummy letter, just fitting into the general pattern. And the general pattern is how to prove for anything that it's a Q. So after line 5, we're entitled to write down for all x qx. And if you think of A as an individual, that step on line 6 should look too quick. But A here is serving as a placeholder. It's an arbitrary thing. And if you can show for any arbitrary thing at all that it's got to be a Q, then everything has got to be a Q. So our universal introduction rule allows us to generalize in this way. From line 5, where we've shown QA, we're allowed to write down for all x, QX. This is allowed because A isn't something we've made assumptions about. This A isn't anything special. It doesn't appear in the premises, and it might as well have been anything else. This is what the rule looks like on the reference sheet. If you have a sentence with a constant, so your sentence A with the constant C, if you have some sentence with some constant in it, you can add a universal quantifier, replace the constant with a variable, and then write down the universal sentence. And it says at the bottom, C, your constant, must not occur in any undischarged assumptions. That means that the constant can't appear in a premise or in the assumption of a subproof so long as you're still inside the subproof. Also, when you use the universal introduction rule, you have to completely replace the constant with the variable. You can't just replace some occurrences of the constant. In our earlier example, it would have followed the rules to do this. On line 5, we have QA. On line 6, we get PA and QA by and introduction. And then on line 7, we get for all x, px, and qx by universal introduction on line 6. What you wouldn't be allowed to do is something like what I've got on the slide here for all x, pa, and qx. Not allowed because the x has to replace every instance of a in the sentence. Now that we've defined the universal introduction rule, let's consider an example. Here it says, show that it's provable that for all x, px, or not px. That is, it's provable without any premises because there's nothing on the left-hand side of the turnstile. We need to prove that it's a theorem. And that means the proof has to have for all x, px, or not px on the last line. And we're going to have to reason backwards because we're going to have to start a subproof somewhere up at the top to give us something to work with. What could we have had that would let us write down for all x, px, or not px? It's a universal sentence, so a natural thought is to use universal introduction. The universal introduction rule says we need an instance of the sentence. For example, if we could get PA or not PA, then we could introduce the universal quantifier and get the sentence we need as the last line. The constant A will work here because it doesn't appear in any assumption or any premise. Note that we haven't actually proven anything yet. We're still just making a plan for how we might be able to end the proof. And the point of the plan is that it allows us to work backwards to figure out what we need to do at the beginning of the proof. So with this plan, we're now looking to show PA or not PA on the next to last line of the proof. How could we show that? Also, since we're proving a theorem, we'll need to start a subproof at some point. Since PA or not PA isn't a conditional or a biconditional, it's natural to look to the negation rules. We can assume the negation of what we want. We assume not, parenthesis, PA or not PA, close parenthesis. Now, in this subproof, we want an explicit contradiction, a sentence followed by the negation of that very same sentence, because the plan is to use negation elimination back out in the main proof to get PA or not PA. So, assuming line 1 gives us something to work with. What can we do with that? Well, line 1 is a negation of a disjunction. And if you look at the rules, you might notice a particular pattern, or you may remember a pattern. De Morgan's rule, that lets us rewrite a negated disjunction as a conjunction of negations. That is, we move the negation inside the parentheses, put it in front of both parts, and we change the or to an and. So now that we've got line 2, it's a conjunction, not PA and not PA. Conjunction elimination lets us write down either disjunct. We can write down not PA by and elimination on line 2. We can write down not PA by and elimination on line 2. So lines 3 and 4 are an explicit contradiction. There's a sentence, not PA, and it's followed by the negation of that very same sentence. We get not PA. So that means back out in the main proof, we can close the subproof, and back out in the main proof, we can now say PA or not PA, negation elimination, and we're applying it to that whole subproof, 1-4, 1 through 4. Now we just have to take the last step in our plan. Having shown PA or not PA, we use universal introduction. So that's universal introduction applied to line 5 to get for all x, px or not px. Notice A here does appear in an assumption of a subproof on line 1. But the rule explicitly says an undischarged assumption. And what that means is the assumption of a subproof that you're still inside of. So for example, we couldn't have said on line 4 for all x, not px, because we were working with an assumption on line 1 that assumed something specific about A. Once we've closed the subproof, once we're back out in the main proof on line 5, A isn't anything special. We don't have available to us any special assumptions about it. And so that means on line 6, we can replace A with a variable and use universal introduction. So this video has covered universal introduction, and we're just a couple of rules away from having a complete proof system for QL.